Hi there, welcome in this new video in the Mechanical Dynamics channel. Today I will present a new application example that will be part of next year's course. And the example is the vibration analysis of an offshore wind turbine. Each year, students following the course are asked as an assignment to illustrate the course on a mechanical system of their choice. In this video, I will present the results of such an assignment as a good practice example for the coming years. Indeed, during the academic year 2022-2023, the students Amal Dabari, Florian Desneux, Paul Gérard and Ayoub Kashaf have worked on the vibration analysis of a wind turbine tower. They have used that example as an illustration of the course, and as you will see in what follows, they have even gone beyond what was proposed by the course. These students have worked in pairs and independently of one another on this wind turbine exam. What is presented next is a compilation of their work. My only contribution has been to look for a publication in the literature that deals with the vibration analysis of an offshore wind turbine. This is the publication I came across, and it studies the vibration analysis of a VESTAS V112 3 megawatt offshore wind turbine. This wind turbine is depicted over here, and this is a picture that I've drawn from Wikipedia. Well, the main advantage of working with the publication, and this will be important if you're preparing your assignment, is that you find realistic parameter values for the system you're studying. Indeed, in the paper you will find that the tower of the offshore wind turbine is constructed from 4 sections of given lengths and wall thicknesses, right? You can also have access to the tower diameter and to certain properties of the material that is used to construct the tower, such as the density and the elasticity modulus. Another advantage of a publication is that they propose the results of their research that you can use to check your own calculations to see if they are realistic. So what we'll do now is have a look at the publication. As you can see, the paper considered 2 types of wind turbines with a cylindrical tower and wind turbines with a conical tower. We'll take the results associated to a cylindrical tower. For both geometries you have 4 segments, right? The first 3 segments have a length of 20 meters and the last one a length of 24 meters. So the tower length in total is 84 meters, right? And you can also have a look at the thickness of the different segments. Well, the main characteristics can be found in the following tables. Here we have, well, the hub height, as I said, 84 meters, right? The tower is made of steel, right? The tower diameter over here. And in the second table, you will find the properties of the material, as I said, the elasticity modulus and the density, and although this is not used in our study, the Poisson coefficient. Well, in our study we'll use a cantilever beam approximation with on top a mass, and this mass regroups the masses of the blades, the rotor and the nacelle, and if you add all those masses together, well, you have 155 tons. Further on in the paper you can find the first resonance frequency in bending with the associated modal shape, and also the second resonance frequency with its associated modal shape. They also present the third resonance frequency, but we'll leave that aside in our study. So what we'll do is compare our results against these 2 resonance frequencies and the associated modal shapes. These are the parameters of the actual wind turbine. This is a bit too complicated over here, so for our study what we'll do is consider the following parameters. So we'll consider only one section of length 84 meters, that the total length of, well, the actual wind turbine, and we'll consider just one thickness of 50 millimeters. For the rest, the parameters remain unchanged. As I said before, we'll use the cantilever beam approximation. We'll assume that the tower is anchored to the ground, and as in the paper, we'll assume here, as we're interested in a vibration analysis of the tower, that there is a mass, that is the total mass of nacelle, rotor and blades, that is applied on top of the tower. Well, of course, the assignment is meant to illustrate the course, so the first illustration that we can make is to use the course to compute the first resonance frequency. And what we can do is replace our system, a cantilever system, in bending with the associated mass, and reduce the system to a mass spring system, a mass that is given over here, and a spring with a stiffness constant that is shown over here. For the spring stiffness constant, we have Young's modulus, we have the length, but we need the area moment of inertia, which is calculated over 4. Well, since we have a cylindrical shape, the area moment of inertia is pi over 4 times the outer radius to the 4th power minus the inner radius to the 4th power. And if you compute this, this is what you obtain. Well, the equivalent mass is given by this formula over here. MT here is the mass of the tower, and MNRB is the mass, or the total mass, that represents the nacelle, the rotor and the blades. This formula has been obtained earlier on in the course, so what we need is to compute the mass of the tower. Well, here you have the formula, you have area times length, so that's a volume times density. And if you do the computation, well, you have a mass of the tower that is roughly 424 tons. Well, once you have the equivalent mass and the equivalent spring stiffness constant, it becomes very easy to compute the associated resonance frequency, and it is obtained over here. As you can see, it's very close to the one that is obtained in the reference paper. Note that in the reference paper they have considered a wind turbine with 4 different sections. And here is the MATLAB code with the different parameters and the computation of the first resonance frequency. To compute the other resonance frequencies, it might be tempting to reduce the system to n degrees of freedom. We have n mass spring systems. Each spring has a stiff constant of n times the equivalent stiffness of the previous slide, and each mass is the mass of the tower divided by n, with the exception of the last mass, where the equivalent mass of the nacelle, rotor and blades is added. We had done something similar for a beam in traction, but here the method is not correct, as only a translational force is transmitted from one element to another, so perpendicular to the beam, and this means that the moments that are at play in the system are neglected, and this is of course incorrect, but we'll see what it gives. And of course, if you write the system in a mathematical form, this is what you obtain, and this system is again in a form where we can use it for a modal analysis. So here's the associated MATLAB code. We'll work with n is equal to 10, but of course you can increase or decrease n. We'll construct first M, then the matrix K. Once we have these, well, we can do an eigenvalue computation of, well, M inverse K, or M in MATLAB /K, and then look at the eigenvectors, and this will give us, well, the resonance frequencies and the modal shapes. So these are the results with n is equal to 10, right? What we see here are the two first resonance frequencies with associated well, modal shapes, and everything has been normalized in such a way that the maximum deformation is either 1 or -1. You can see that the two resonance frequencies do not correspond to the ones that are obtained in the reference paper, and this is particularly true for the second resonance frequency, so there is a huge discrepancy. If you look at the deformation at the base of the tower, you can see things that are looking a bit suspicious, right? Because you would expect a more gradual deformation, and this is because we have reduced our system to n degrees of freedom without taking into account rotation of the elements. To take into account translation and rotation, we can use a so-called finite element method that was not covered by the course. But thanks to our 4 students, this will change, as this will now be explained in this video. The theory will be provided without explanation of how it is obtained. If you want more information, you can refer to the following reference. So we'll start with a finite beam element in bending, and of course in our example we'll have n such elements. Each element is characterized by a number of parameters such as mass, length, elasticity modulus, and area moment of inertia. Each element has 2 nodes, node 1 and node 2, and each node has 2 degrees of freedom, 1 in translation and 1 in rotation. Well, the theory shows that for one element you can write the following equation here that is suited for modal analysis. The matrices ME and KE are given over here and depend of course on the parameters that are given over here. I have rewritten things slightly by partitioning the matrices in such a way, well, that the variables, the 4 variables that you have for one finite element, are organized per node. So here you have the 2 variables associated to node 1, and here the 2 variables associated to node 2 per node. So you have a variable in translation and 1 in rotation. This will facilitate the analysis if you have more than one finite element. We know that we'll have n finite elements, so we need to understand how we need to deal with a situation where we have n finite elements and how we can construct a description for this situation, right? So we'll first consider 2 successive finite elements in bending. So here you have the first one. Remember that we have 4 variables associated to this first finite element, right? And they are stacked in Q1 and Q2, and this is the description for this first finite element. We'll have something similar for the second finite element, and here we have the variables that are stacked in Q2 and Q3, and as you can see, well, Q2 appears in both descriptions, right? And if you want a global description, well, it's kind of juggling with these matrices, and you'll see that you can rewrite this as follows. It's kind of easy to see what's happening, right? So the first line over here, M11 Q1 double dot, M12 Q2 double dot, and so on, you can find it over here, right? First line over here, first line over here. I say line, but this is also a matrix differential equation, right? So this was this line over here. The last one, it's kind of easy to see where it appears. It appears over here, right? M21 Q2 double dot plus M22 Q3 double dot. Well, you can kind of see this appearing over here. This one here, over here, well, you see it appearing in here, right? But you see it also appearing with this line. You see actually the sum of those 2 appearing in this line over here. So you have also the second part coming from this equation over here, right? So, for instance, if we take M21 Q1 double dot, M22 Q2 double dot. This is what you see over here, right? Right, and these ones, you see them appearing over here and over here. Whereas the second line, you see it appearing over here, M12 Q3 double dot, etc. And then for the rest, you see them appearing over here and over here. Okay, so you can kind of see how it's not that difficult to go from this description, where you have two separate descriptions per finite element, to a global description for the two successive finite elements. You can kind of see that for a given configuration with n finite elements, we have 2 times n plus 1 variables. In these two descriptions here, we have n is equal to 1, so we have 4 variables and 4 variables, right? 2 variables in Q1 and 2 variables in Q2. If we combine the two finite elements, so here we have n is equal to 2, then we have 6 variables, right? 2 in Q1, 2 in Q2, and 2 in Q3, right? And to write the global description, well, you make a matrix of dimension full of zeros of dimension 2 times n plus 1, and then you stack the matrices corresponding to one finite element in the matrix, right? You can kind of see this over here. So here we have this matrix over here. This is the first one. You see it appearing over here, right? And the second matrix that you see over here, well, you have to stack it in this big matrix, but you have kind of shifted, right? And you can see it appearing over here. So you can kind of see that to construct the overall M matrix, well, you can do this very easily from the elementary M matrices. Let us return to the situation of interest, which is the tower with on top a mass, that is the total mass nacelle, rotor plus blades, right? And the tower is cut into n elements as shown over here, and the situation that is depicted corresponds to n is equal to 4. And similarly, you have the situation here of m and k for n is equal to 4 to explain things, right? If you have cut the tower into n elements, you'll have n plus 1 nodes. Since you have 2 variables per node, one in translation, one in rotation, this means that you have 2 times n plus 1 degrees of freedom, right? So this means that you need matrices k and m of dimensions 2 times n plus 1. You can start with matrices filled with zeros, right? And then you have to stack the elementary matrices ke, me. So here you'll have 4 of them, of course, and here you see the first one, right? The second one, well, you kind of shift on the diagonal by 2 elements, right? And you see it over here. That's the second one. The third one, you see it over here, and the fourth one, you see it over here. So to construct k and m, it's kind of easy. I've done it for k, but you have something similar for m. Now, we have to remember that the mast is embedded at its base, so we lose 2 degrees of freedom. They correspond to the first node, so we lose a variable in translation and one in rotation. This is what is shown here by those lines in red. You have to take them out, and instead of having matrices of dimension 2 times n plus 1, you have matrices of dimension 2n, right? 2 times 2n times 2n, of course, because the matrices are square. Also, we have to make a little adjustment in the M matrix because we have the total mass, nacelle, rotor plus blade, that is added on top. So we need to add on the diagonal element that corresponds to the node n plus 1, to the variable nu. We have to add this mass, and this is why over here we have added this matrix over here. So here we have constructed the overall matrices K and M for a situation where we have n is equal to 4, but you have kind of understood now that you can generalize this for any n. Well, you can generalize this very easily using MATLAB code. Here again we'll work with n is equal to 10. So here you have all the variables, and here you have the elementary matrices Ke and Me. So we can create the matrices K and M. We start by creating big square matrices filled with zeros, and they have dimension 2 times n plus 1. And then you have to stack the elementary matrices in there. You have to do this n times, and then you start at the top left corner, and then you kind of shift on the diagonal by elements of 2, right, as we have shown in the previous element. At the end of this operation you have K and M, but remember we have to take into consideration the total mass, nacelle, rotor and blades, and we have to take into consideration that we have kind of lost the variables associated with translation and rotation corresponding to the first nodes, right? This is what I had done in the previous slide that was shown with those red lines. So we have to take out the 2 first lines and the 2 first columns in M and K. Once you have done these operations, you have M and K, and then you can do, well, the standard operations to compute the eigen frequencies and the modal shapes. Well, this is what you obtain if you run the code with n is equal to 10. You have the modal deformations, and here the 2 resonance frequencies that are very close to the ones obtained in the reference paper, and you can kind of see that the deformation at the base is as expected, in the sense that it's more gradual. And if you would run the simulation with n much higher than 10, okay, you would see this even more clearly. One aspect that we have not discussed is that the shear effects are not taken into account. It is possible to find in the literature, well, formulas that obtain Ke and Me as a function of the shear modulus G. We have not done this, but it's possible to adapt the model in such a way as to take into account shear effects. We will see that if we do a study using SolidWorks, shear effects are indeed taken into configuration, and we'll do this in the next slides. Well, so far we have used the following description. So this is our matrix M, so Q double dot plus K, Q is equal to 0. But what we can do is replace this and add an input here. So this one has dimension 2n times 2n. So this means that this one is a vector of 2n elements, right? And x, if you look at it, well, it's composed of a force, for instance, that would apply on the second node, a moment on the second node. Remember that we have lost the first node because the beam or the tower is anchored in the ground, and you can do this up to node n plus 1. So you could apply a force on node n plus 1 or a moment on node n plus 1. So you can do this and use the model, the corresponding model, for simulation. And what we'll do here is compute an impulse response. If we put a force here on the node n plus 1, right? So we have this description over here. We go to the S domain. Our input will consider all zeros except the one that I've shown over here, right? And then we'll simply use the impulse command of MATLAB, and we'll kind of see what happens. So here's the code. We'll run the simulation for 10 seconds with a time step of 0.01. We're using the impulse command. We'll have, well, the Q vector at every t, and in this Q vector we'll select the variables associated with translation. There are n of them, and we'll show them for every t, and then pause a little bit so that you have kind of an impression of what's happening on the actual system. So let's run this code and see the result. So this is what happens over here, and here of course you see the scale of the deformation. One team of students, the team of Florian Desneux and Ayoub Kachaf, had also checked their results using SolidWorks. So what I've done here is take their file and adapted it so that it would correspond to the wind turbine that we have studied in this video presentation. The advantage of using SolidWorks is of course that you can check the results, but that you can also take into account the shear effects. We'll see here that in fact they can be neglected because we obtain kind of very similar results to the ones that were obtained using the finite element method. So we can check the parameters. We have 84,000 millimeters, so a height of 84 meters, and here we have on top of one another the external and internal diameter. So the external diameter is 4,176 millimeter, and you have a difference of 100 millimeter, which is then the thickness, which corresponds to 50 millimeter. You can have a better view from above, and then here you see indeed the external and internal diameter. We can also have a look at the parameters corresponding to the material that is used for the tower of the wind turbine. We can see that it's related to steel. Here we have indeed Young's modulus that we have used previously, and the density, right? But you can see here that there also is an additional parameter corresponding to the shear modulus G that I had introduced before. So indeed shear effects are taken into consideration. Now that the model is ready, we can have a look at the frequency analysis and do a simulation. In fact, everything has already been prepared by the students. All I had to do is, well, change the mass here on top of the tower. You can kind of see here that the tower is anchored to the ground, right? And that a mass has been added on top. Top is 84 meters, right? And this mass corresponds to 150,000 kilograms, right? So now we can, if we want, run the simulation, but this has already done before, so we can have a look at, well, the first resonance frequency, and this is very close to what we had computed before with its associated modal deformation. And then we can have a look at the second resonance frequency, and again this is very close to what we had computed using the finite element method, and again we have the associated modal deformation. So these are the two results that we had obtained using SolidWorks, the first resonance frequency and the second resonance frequency. And they are of course very close to what is obtained in the reference paper, and also very close to what was obtained using the finite element method. Remember that in the paper they used a tower in 4 sections with different thicknesses, right? And as we had seen and expected, also in SolidWorks the deformation at the base is gradual, okay? And as we have seen, shear effects are indeed taken into account. This concludes this video presenting an application of the course to the vibration analysis of a wind turbine tower. I want to thank the 4 students whose names you see there on the screen for their very nice example that goes beyond what was initially proposed by the course. Hopefully we'll meet again next year with another application example proposed by next year's students.